Copy this one down. I'd like you to give it a try, at least to see where could I go from this and what can I learn from the information given, and then we'll work it together to figure out the ultimate answer and how to solve a more complex problem like this. So I see a lot of good starts. I want to give you a nudge towards finishing this on your own. We've got a 1 kilogram hunk of lead. So what's that 1 kilogram represent? Mass. It's a mass. Here. Okay, we know specific heat is 128 joules per kilogram per degree C. What does this 1.75 represent? Is that a delta T?
No.
Why? How do you know, Drew? What tells you that it's not a delta T? It's in liters, yeah. It's in liters. It's what would delta T be in?
In degrees Celsius.
Degrees C. So it's liters. That's a volume, which tells us a mass of water too, right? So I'm going to have to label these a mass of water, a mass of lead, and specific heat of lead. So the mass of water is, if it's 1.75 liters, it's 1.75 kilograms. What about this decrease in temperature by 45 degrees C? What is that? It's a change in temperature of what? The water.
Yeah.
So we know a delta T of water is negative 45 because it's cooling. What are we trying to find in this? Temperature change of the lead. So that'd be a delta T of lead. Fine. No.
All that to do
But it's still annoying, but it's. Oops.
It's Monday.
You think I do? Toby does. Brown. Who? Brown. Who's Brown? The boy. The boy. That's the boy's name. I haven't seen the boy.
There we are. I have to write more slowly. Okay, we want to find the delta T of lead. Well, given these two things, if we want to find the delta T, what else are we going to have to know? Well, if we knew the temperatures, that would be a very easy way to go. But we don't have enough information to directly tell the temperature. Yeah, Jeremy. Why do we need the C of water? We do know it. It's 4,186 joules per kilogram per degree C. Why do we need that? Okay, we can find the thermal energy of the water because it's M times C times delta T. Since we're so limited in space, let's just do that without writing it all out. We've written out what those pieces are. So we take the M, 1.75 kilograms, times the C, 4,186 joules per kilogram per degree C, times our change in temperature, negative 45. We get a negative 648, I'll call it. What units? Joules. But how does that help us now?
We
What
plug it
number is
in.
that?
Why would we plug it in?
Because that's
This is
of the water.
This is of the water. This is how much energy the water lost. So it's M times C times delta T for the water. And so we can tell how much energy the water lost. That is a 6. I started writing the 4 first, and I can't erase easily here. So the fourth digit is a 6. But now how does that help us? But do we know TE yet? We know how much thermal energy is involved with the water. So you're right, I think you're right, we need to know the thermal energy of the lead. But what can help us do that? What does this negative mean here in thermal energy? It's going down. Thermal energy is going down, which means the water was losing it. What was the water losing the thermal energy to? The lead. So conservation of energy, you can't create or destroy energy, but you can transfer it. If the water lost this much, how much did the lead gain? That much. The only difference is it's positive. The lead was gaining the same amount. So when you mix two things, that's a 6, 4, 8 of different temperatures, the hotter thing will lose a certain amount of temperature. The cooler thing will gain the same amount. So now we do know everything except the change in temperature. If we take this formula, and again I don't have room to do it, if we take our formula, TE equals MC delta T, and we want to solve just for that delta T for our lead now, we'll have to divide by both of those. And we'll end up with the thermal energy, this time of the lead, over the mass of the lead, times the specific heat of the lead. And again, because of space, I won't write all of it out as I usually would. We'll take the thermal energy, our 329,648 joules, divided by the mass, which is 1, and divided by the specific heat, 128, and we get, holy moly, a big number.
Oh my god.
2,575. What units would that be?
Joule. No. Yep.
Joules.
No.
No.
No, it's degrees Celsius.
So if we divide these out,
That
we
would
get the
be
degrees.
super high.
Does anyone see anything wrong with that?
That's not how high Celsius goes, right?
There isn't actually a maximum on the Celsius scale.
That'd be high.
That's pretty high. That would be pretty high.
What was happening to the water though? What was happening to its temperature?
Degrees. Degrees.
It was decreasing, it was getting cooler. So that must, and this is getting warmer. The water has to be somewhere in the range of 0 to 100 degrees to be water. So how cold must this have been at first? Must have been somewhere on the order of negative 2,500 degrees to do that. Does anyone have a problem with that? All okay with that?
Yeah.
We're all okay with that. What does that mean?
That's the coldest it can go.
Coldest it can go. So are we still okay with the negative 2,500 degrees for the lead?
Nope.
Yeah, no, it wouldn't, we couldn't actually get that to work, that problem to work physically. Yep.
How can that be like a limit? Can't be colder?
What is temperature?
It's like measure how much energy.
How much energy? So is there a lower limit to the amount of energy something could have?
I guess so.
What would it be? What is the lower limit of energy that anything could have? What is the fewest number of hairs you could have on your head?
0.
Why 0? Why not negative 10? You can't have negative 10 hairs on your head, right? No, of course. And the same thing with energy. You can't have a negative energy. The lowest the energy could be is 0, and that's what absolute 0 refers to. So that's how we know that that's the absolute minimum, because we couldn't take out any more energy, there'd be none left. And that occurs at negative 273. So our problem here is certainly this change in temperature of 2,575 degrees wouldn't be physically possible. It's still an okay, well, because I wrote it without thinking of that, I think.
Okay.
That's just the way it goes. Okay, and that was our last example. What I want you to keep in mind, we're going to have the rest of the time to work on the homework, which is a Moodle homework, do it, check your answer, that sort of thing. But keep this kind of thing in mind, because the end problems will be challenging like this. They'll give information about one substance that's mixed with another at some times. You might have to rearrange it and think like that. You'll also have to rearrange our formula, which I'll write up on the board, to find different things. If you're trying to find, if it says what temperature did it start at or what temperature did it end at, you're always going to be looking for a delta T first, and then use that information along with the other givens.